So in this module, which is the Wide Area Network Design module, we are going to look at several different aspects of wide area network design. We're going to be talking about specifically things like service provider managed VPN solutions, primarily MPLS, right, the multi-protocol label switching. We're going to look at designing enterprise managed VPNs, some of the design elements anyway. We'll also take a look at incorporating resiliency into the design, and then how do we handle the edge and partner connectivity, and then we'll take a look at enterprise network using the SDN principles, software-defined networking principles. This is one of those new topics. It's part of the new version of the CCDP, and it is an interesting topic, and it gets into those SDN principles that we don't see in a lot of the other Cisco courses. We know that in modern networks today, connectivity to these different locations, connectivity to these different branches is dispersed, right? And we're connecting multiple offices or multiple locations that are geographically dispersed. The applications themselves usually reside inside of a data center, and it's very critical for the network to provide some sort of reliable connections or reliable connectivity to the data center itself. The WAN network, or the wide area network that we're installing, is used for connectivity between that data center and those remote locations. And we know that we have lots and lots of different options with regard to how we implement the WAN. The decision point that we have is based on usually the reliability, the robustness, the scalability, and quite frankly, the cost associated to implementing these WAN technologies. So we're going to take a look at some different advantages and drawbacks to each technology, and then we'll also take a look at how to implement each of those technologies in this module. The first lesson that we're going to cover in this particular chapter or this particular module. So in lesson 1, we're going to talk about service provider managed VPNs, we have a few options in this regard, right? We can talk about different types of WAN connections, but we'll look at things like layer 3 MPLS VPN architectures. We'll talk about how that architecture is constructed, right? How an MPLS VPN architecture is constructed. What are the actual components of that architecture? What is the role of the PE router in this architecture? The PE is the provider edge router. We'll take a look at route distinguishers and take a look at how route distinguishers fit into the operation of this MPLS VPN. We'll look at route targets, route target operations, and then we're going to apply discussions about EIGRP as part of that PE to CE routing protocol connectivity. So the provider edge to the consumer or customer edge device, OSPF, PE to CE as a routing protocol, and multi-protocol BGP as a PE to CE routing protocol. And later on, we'll actually talk about BGP as a protocol in general. We'll take a look at MPLS and VPN routing propagation and how that's going to work. We're going to describe packet forwarding through the MPLS and VPN backbone. And then we'll wrap up this lesson by talking about the wired service, VPWS, and the VPLS service as well. And then we'll take a look at the difference between VPLS and VPWS, right? So there's a lot of stuff that we're going to cover just in the first lesson of this particular module, this wide area network design module. There are lots and lots of ways that we can connect our main site. We can build our own infrastructure, although that's very cost prohibitive. If we have, say, several different buildings that are geographically dispersed, but they're relatively close to each other, we can build our own infrastructure, right?
Hello, Scott. I lost audio.
Yeah, the same here. I think he's dropped off and talking back.
Okay.
Of the WAN topology takes care of the WAN connectivity, and that means that the service provider is going to be responsible for transferring packets from one side of the network to the other side of the network. Obviously, there are lots of different options as to what transport the service provider decides that it's going to use. It could be, say, for example, hold on one second. So as I was saying, the provider has lots of options with regard to how they can transport the data. Obviously, the most prominent solution that we have today is multi-protocol label switching, and that's what we're going to focus on. But you could use relay, you could use ATM, you could use other kind of simulated point-to-point connectivity options, but we're going to focus primarily on the multi-protocol label switching because that's what is more popular today than any other option. There's a couple of reasons. Number one, it's a very efficient protocol, right? It provides the ability to transport data efficiently from one side of the network to the other. In addition, it supports quality of service. Granted, we only have 8 levels of quality of service if we count level 0, but it's better than, say, just using a discard eligibility bit in frame relay and maybe some forward explicit congestion notification or backward explicit congestion notification. So lots and lots of choices, all right? Let's start by taking a look at what the decision points are and how I will make my decision on what service I'm going to use. There are several different major decision points when you're choosing a WAN connection that you want to use. And they can include things like service availability, financial considerations, technical considerations, and so on. When you're designing your WAN network, you have to check what services are available from your service provider first. Obviously, not every service provider is going to have all services available at every customer site. That's why you'll see a lot of major corporations and businesses will try to utilize a tier 1 service provider to connect their locations because they know that they're going to have the most options with regard to service transport and what kind of services can be transported across the WAN. You may actually be forced, if you're in a rural area or your locations are fairly remote, to combine multiple services, right? So if you have different options, if you're provided with different options across the board, there are a couple of major decision points that you have to use to choose whatever WAN connection you want. obviously, I kind of joke about this in my CCNA class a little bit. The 7-layer OSI model is always actually 9 layers because layer 8 is budget and layer 9 is politics. But financial aspect is a very important component when you're choosing your WAN connection, right? You want to compare the cost of the services, the cost of equipment, the cost of maintenance and operation, and also the cost of training, right? Training your individuals or your staff in choosing the right or being able to support the right WAN technology, all right? The other important aspect is what we call the long-term lock-in value, or not value, but contract, right? When you establish a layer 3 VPN, it's becomes a lot more difficult to change service providers because you may have to readdress all of your CE devices, you may have to establish new routing policies, you may have to even establish new design elements, right, and add components to the network. So this long-term lock-in is something that kind of gets created when you commit yourself to a particular VPN technology. It's much easier to change the provider if you're doing some sort of layer 2 VPN because over the transport is basically a switch. It's a layer 2 transport as opposed to a layer 3 transport. So whenever you can control the routing yourself and you're not reliant on the provider to provide that routing function, it gives you a lot more flexibility and a lot more control. There are also many different technical aspects when you're choosing the WAN connection as well. I mean, we talked about long-term lock-in. That could be kind of considered a technical aspect, but obviously the financial aspect is not really technically driven, right? But as you can see from the slide here, we have several different considerations from a technical standpoint. For example, convergence is a consideration. When we're choosing a layer VPN, the routing is under the service provider's control. They're participating in the routing environment, in other words, which includes whatever aspects of routing design that we have to concern ourselves with, all the stuff that we talked about in the previous 2 chapters with convergence time. If we're choosing a layer 2 VPN solution, which we can do with MPLS as well as other functions like frame relay, we are responsible for the routing in this case, and then we can control timers, we can control the things that we talked about yesterday with the link state advertisement, propagation time, and the spanning tree, shortest path first algorithm, timers and whatnot. All right. Another aspect is scalability. When we choose a layer 2 VPN, we have the scalability issues in full mesh topologies that we have to concern ourselves with, right? Getting a full mesh design in a layer 2 VPN environment can be very challenging. There are a lot of considerations that we have to take into account. Routing protocols, for example, may fail due to having too many neighbors or too many adjacencies. They could get overloaded and so on. With a layer 3 VPN solution, all of the customer edge devices only have an adjacency with a provider edge device. So it's a much more scalable solution in that we're only managing that relationship from the CE side to the PE side. We're not concerned with what's happening with all of or peering relationships between every router at every location. Quality of service is a very important aspect as well, right? We know that WANs, generally speaking, have lower bandwidth or have fewer resources available than, say, a LAN or a metropolitan network. So oftentimes in the case of a WAN, we need some sort of QoS to prioritize real-time traffic or mission-critical traffic or whatever traffic we deem necessary. Service providers often offer some sort of QoS service for the traffic that they're transporting across the backbone. And again, that's why MPLS is such a popular WAN protocol, because it allows us to incorporate quality of service as a transport mechanism across the backbone. It's got inside of the MPLS header, there is a 3-bit field called the experimental field, EXP field, and that field is specifically designed to allow for marking of MPLS frames, packets, that allows us to prioritize those packets through the service provider network. Now, obviously, if the service provider is providing these kinds of services, these QoS services, oftentimes they're going to charge for those services as well, right? They're going to charge you a premium to provide enhanced services across their backbone. Service level agreements are very important as well. Many service providers offer some sort of service level agreement for their services. The SLA obviously needs to be reviewed so that you can maintain minimal service level service level function across the network, and there most likely would be some sort of contract tied to that to identify what occurs, how much you have to pay for that guaranteed service, number one, but what should occur if those service levels are not met by the service provider. Could be mean time between failure that you're looking at. It could be round trip delay. It could be jitter. It could be packet loss. There are many, many different things that can be incorporated inside of a service level agreement. Another consideration for, or technical decision point for deciding what WAN technology to use is to identify what traffic is supported across that WAN, right? And a lot of times we don't really necessarily think about this because we just generally assume that most traffic is going to be allowed across an IP connection. But it's actually not always the case, right? And you might think, well, what kind of traffic are we talking about? We're talking about multicast traffic, we're talking about anycast traffic, broadcast traffic, and so on. Obviously, with modern routing protocols, it's very important that we're able to transport things like multicast traffic. And some service providers actually support multicast traffic. Some service providers do not, right? If we're running a layer 2 MPLS VPN or any kind of layer 2 transport, like a frame relay transport, multicast is specifically needed because we have to establish peering relationships between the routers over this layer 2 network. Hello packets and queries and updates or and replies, these are often multicast type traffic. So that's an important consideration. Another consideration is our maximum transmission unit length. We want to try to avoid as much as possible any need for packet fragmentation because it takes time to fragment packets, it takes time to reassemble packets, it takes CPU cycles, it takes processing power. So we need to know the MTU size of the service provider network so that we can set the appropriate MTU values on our network, and maybe it's smaller frames than we normally are used to seeing in an Ethernet environment, or we may be able to forward jumbo frames and be able to support the use of jumbo frames across the WAN. So these are just some technical considerations to think about when you're selecting a VPN solution and you're designing a VPN solution. The most common implementation of a layer 3 VPN is an MPLS VPN today, multi-protocol label switching. MPLS is a technology that is used to forward packets over what we call the core network. The core network is the service provider network, right? And we'll see this later on as we kind of, I think the next slide, we actually see a visual representation of the working components of an MPLS network, right? But that forwarding technology, the way we forward packets over the core network, is through the use of these things called labels, all right? The whole point of an MPLS VPN is to provide a technology that provides a bridge between private networks, your local networks in your facility or your locations, over some sort of public domain. And that's the general goal of any kind of VPN solution. All right. We know that a layer 3 MPLS VPN allows us to connect multiple customer sites together. The solution itself, if we extract or remove the client-side components, the solution itself uses two core technologies. The MPLS is used to forward the packets through the service provider core. So we're not running MPLS at the customer side. We're not even really running MPLS at the provider edge side of the router, although that's where the initial MPLS configuration takes place. MPLS is primarily used to forward packets through the core of the service provider network. The second major component is something called MPBGP, or multi-protocol BGP. That's used to exchange the customer routes between the service provider edge routers. So if you imagine you've got, I'll do a little diagram here. You've got your customer router connected to your provider edge router. Inside the cloud, well, let me do that again because I kind of didn't draw that right. The cloud includes the provider edge router. Well, you've got a bunch of routers in between that are connected, and those routers, that's where your MPLS is running. But then you've got this MPBGP that is running between this router and this router. And the whole goal of MPBGP in this case is to exchange routes learned from this customer edge router over to this customer edge router. So we're not running BGP inside the core. That doesn't exist. We're running BGP between the provider edge routers. And we'll see this on the next slide. Their diagram is a little bit better than what I just drew, but I wanted to give you kind of a general idea of what they're talking about here. When we say that BGP is used to exchange customer routes, it's used to exchange customer routes specifically between those PE routers. All right. From a customer's perspective, MPLS VPN, pretty basic. We connect our equipment directly to the service provider's network. We use some sort of dynamic protocol, although we don't have to, we generally do, some sort of dynamic protocol to transfer routes to the provider edge router using either a protocol that the provider chooses, which would typically be some sort of IBGP or eBGP communication. We can use EIGRP, we can use OSPF. It really depends on the service provider, right? But there is some exchange of information from the provider edge router to the customer edge router. And that's not generally the same IGP that we're running inside of our network. It could be the same protocol type, right? It could be OSPF, and we maybe happen to be running OSPF as well. But usually the provider is going to choose something like, well, a protocol that they, understand, which is usually BGP, all right? Regardless of whatever protocol is chosen, both parties need to agree on what IGP parameters they're using to communicate those routes from the customer edge router to the provider edge router. Once the service provider receives the routes from the customer through that IGP, it has to transfer those routes into other locations. In other words, we have to send those routes across the service provider network so that those routes can be transferred to other locations. The challenge that the service provider has in that regard is that oftentimes customers are using private routes. They're using RFC 1918 addressing, and multiple customers might be using the same RFC 1918 address space. That being said, there has to be a way to distinguish one customer from the other. We use virtual route forwarders. We use essentially unique IDs to identify each client or each customer. Okay? When the service provider receives the routes, it has to transfer those routes to the other locations. BGP, specifically MPBGP, is used for this particular task. So we can connect a whole bunch of sites together because MPBGP is designed to work with very large databases. All right? If we're using a Layer 3 MPLS VPN, if we're choosing to implement a Layer 3 MPLS VPN, we are very dependent on the service provider to provide that routing, right? Which makes it difficult because if I decide that I want to change service providers or I want to incorporate additional services, that service provider has to support those services. Because the provider is actually participating in the routing. The service provider network is actually technically then the core of your WAN. So routing convergence, reliability, the things that we normally would control if we're running something over a Layer 2 VPN is out of our control, and it's dependent upon the service provider to ensure that we're getting those kinds of services in the core of the network. All right? So what you're seeing in this architecture is really the topology that I was describing in the last slide, right? And we'll break down each of these components here, and hopefully visually you'll get a better representation of what we were talking about on the previous slide. There are essentially 5 major components to an MPLS design. The customer's network, that would be your customer controlled domain. So this network here, oops, let me change my pen color back. This network here, this network here, this network here, this network here. So that's your core IGP, your customer IGP, where you're creating your subnets, creating your networks, and so on. The second major component is the customer edge router. The customer edge router is 100% under customer control, and it's located at the edge of the customer's networks. And these routers have physically a direct connection to the service provider network. It could be a T1, it could be a twisted pair Ethernet connection, a fiber optic cable connection. It just depends what the last mile is. It doesn't necessarily have to be an Ethernet connection, but typically it would be. There would be some sort of Ethernet handoff, whether it's fiber or copper, between the PE router and the CE router. But that is, and by the way, that last mile might not even be provided by the core service provider, right? Last mile is generally controlled by geography, and the local carrier is going to provide that connectivity. So there are partnership agreements that service providers have with local carriers to be able to provide that connectivity. Okay? The next component is the provider edge router. The provider edge router obviously is located at the edge of the MPLS service provider cloud, and it's connected to the CE router on the LAN side, or on the, outside of the cloud, and then it's connected to these P routers on the inside. The P routers are located in the core of the provider network, and they're connected to other P routers or to PE routers. The goal, of course, of a P router is transport. The customer is often not even aware that those P routers exist or how many P routers there are. That is part of the service provider's core network. Okay? The provider network itself is really what we call the provider-controlled domain. It consists of those PE routers and the core routers, and that's the transport that allows us to connect our customer sites together. All right? So if you look at the diagram here, you can see how we have BGP running only between the two PE routers. This is where our MPLS is running inside the core. And by the way, it's not only MPLS that's running inside that core. There is also a core IGP running inside that core. So the service provider is running some sort of layer 3 routing protocol inside the core as well. Usually that's going to be ISIS or OSPF or some other core IGP protocol. Very rarely would it be BGP. But again, that's hidden from the customer side. Now the customer has to push all of their routes that are going to be accessible at the other customer sites from the CE router to the PE router. And the customer is actually responsible to implement whatever routing protocol is required to accomplish this goal, right? Usually the provider is going to be identifying to the customer what protocol to use and the parameters that are going to be used for exchanging routes between those routers. In my experience, it's typically been BGP, some sort of IBGP communication using private autonomous system numbers, but it doesn't have to be that, right? It could be RIP for all we care, right? The goal, though, is to get routes from the CE router to the PE router. But the key is that the customer and the service provider have to choose or have to agree on what that protocol should be. The customer then injects all the routes that are needed into that routing protocol, usually through some sort of redistribution, right? I might be running OSPF as my core IGP, and then I might be running BGP as my protocol to exchange routes between the customer edge and the provider edge router. All right? In some cases, it could even be the same instance as the internal routing protocol, but that's very, very rare because we don't generally want the provider participating in our internal routing as well. So we'll usually have some sort of secondary routing process between the CE and the PE device. Okay? In the end, though, it's just a matter of agreement between the customer and the provider as to what we choose to disseminate that routing information from the customer to the provider. The CE router peers only with the PE router and doesn't peer with other CE routers. Again, this would only apply if this is a layer 3 MPLS VPN architecture. All right? So the CE routers are not peering with other CE routers. We're not exchanging routes directly from CE router to CE router. The goal of the provider edge router is then to take those routes that are being pulled from the CE router and redistribute those customer routes to the BGP routing protocol process, the MP BGP routing protocol process. Those redistributed routes are then carried to the other PE routers using MP BGP. So this PE router here has a BGP peering relationship with this PE router here. We're not running BGP in the core, right? We're using some sort of IGP, core IGP, to transport the BGP messages between the PE routers. And we're using MPLS to switch packets more quickly and more efficiently through the service provider core. All right. So the routes get redistributed from MP-BGP into some sort of IGP, right? So we've got internal routes getting redistributed at this point, getting exchanged through some sort of IGP process here, getting redistributed into BGP at this point. Those routes, or the knowledge of those routes, are being exchanged through BGP, again being redistributed into the IGP, and then redistributed back into the other customer site. So there's a lot of moving parts in this particular implementation, right? The MP-BGP sessions, like I said before, are only established between the PE routers. So there is an additional component, right? It's the service provider core IGP component, which isn't actually depicted on this diagram, but it does exist, okay? So that is a visual representation of this architecture that exists within the MPLS domain. The challenge that we have, in addition to servicing these clients individually, is that we may be servicing multiple clients at the same time. And if I've got customer 1 here, and they're using some sort of RFC 1918 addresses in their environment, and then I've got customer 2 also utilizing RFC 1918 addresses, which is very common. Most people will implement private addressing inside their LAN. It's highly likely that those customers are actually utilizing the same address space, okay? So I can't simply exchange customer routes without having some way of distinguishing the difference from one customer to the other in the global routing table and in the provider edge and provider routing functions. So the PE routers in our MPLS VPN network are really kind of the most important components in the MPLS VPN architecture. They perform a lot of different functions that are required in order for us to facilitate this overall architecture. Now we know that one of the primary goals of the PE router is to get routes from the customer edge router. But an extension of that is that the PE router has to isolate customers' traffic somehow. The routing should be separate and private for each customer on the PE router. So each VPN needs to have its own routing table, essentially. This routing table is called a VRF routing table, a virtual route forwarding routing table. All right, so each interface towards the CE router can belong to only one of those VRFs. So we're going to have a separate VRF for each customer. All right, that means that each packet that gets received on the interface is identified as part of that particular VRF. All right. Essentially what we're doing is we're virtualizing routing for each customer. So it would be similar to saying each customer has their own router, basically. All right. The other thing that the PE router has to do is it has to establish the IGP routing adjacency with the CE router so that we can actually get the routes from the customer. All right, so we have not only the global routing table that we see listed there, which allows us to transfer routes across the service provider core, we have customer routing tables as well. Those routes are actually installed in that isolated routing table that we talked about in the previous paragraph, right, in the previous discussion. We could isolate customer routes by using static routes if we so choose, but usually that becomes kind of an operational burden and it doesn't really scale well, so we don't see that too often. But here's the key to this whole thing. Because the customer routes are isolated in these virtual route forwarding instances, different customers can have the same address space, which then provides the ability for the service provider to service potentially hundreds or thousands of clients at one time. All right. All right. Now the PE router then in turn exchanges routes that get installed into those VRF routing tables, which are kind of depicted here in the diagram. This would be a VRF routing table. This would be a VRF routing table. But those routes need to go into this global routing table. All right. Well, before we can put those into the global routing table, we have to essentially change those routes to make them unique, right? Because the global routing table is only a single routing table. The problem is that when BGP carries these different V4 prefixes across the service provider network, they have to be unique, right? As long as they're separate in separate VRFs, there's no need to worry about whether or not the uniqueness exists, because they're logically separated into different routing instances, right? But as soon as I distribute those routes into the global routing table, into this global routing table, then I run into the problem of uniqueness, all right? Especially if customers have overlapping address space, the routing would not work. It just simply wouldn't work, okay? So to solve this problem, particularly in MPLS VPN, there was a concept of what we call a route distinguisher, or RD, that was introduced to solve the problem. The basic idea of a route distinguisher is that each prefix that gets distributed from the customer routes, so those VRF routing instances, receives a unique ID. And the goal of that unique ID is to distinguish the one prefix from another, even if they're the exact same routing prefix, like a 10.0.0.0/8. So what happens is the router prepends this route distinguisher, and we'll see what that route distinguisher looks like on the next slide, but the router prepends this route distinguisher to the route, and we get something called a VPN V4 address. So whenever you see a reference to VPN V4, you know that is an IPv4 route prefix that has had this route distinguisher attached to it. All right. The PE router has a global routing table as well. Obviously, the global routing table is used to communicate with the other PE routers. So this global routing table is part of that core IGP that allows for reachability from one PE router to the other PE router. Remember, in BGP, we'll talk about BGP later, but remember, in BGP, peering relationships can be virtual. They can be physical, but they can also be virtual. So we're peering between those two PE routers, but there has to be reachability. There has to be connectivity in order for that to happen. And that reachability, that connectivity is serviced by our core IGP. So the global routing table is what allows those PE routers to communicate with each other. The other thing that global routing table is used for, the other thing that the PE router provides is the initial MPLS label configuration, right? So this is where the first label gets applied, and additional labels get applied for each customer as the routes get sent through the MPLS network. We'll talk about the label function a little bit later on. All right. Any questions so far? All right.
So each customer has their own VRF, is that right?
Correct.
And then you're saying all the routes from that VRF have to get pushed over or leaked, I don't know the term, over to the global routing table with the unique identifier?
They don't go into the global routing table per se. They get exchanged into MPBGP with the route distinguisher.
Okay.
And then MPBGP. So the P routers don't know anything about the customer routes. Does that make sense? The P routers themselves are not going to have a routing instance or any kind of route that from the customer side. The only exchange of customer routes is between the PE routers. Does that make sense?
Yeah.
The P routers are used simply for transport. So it doesn't, these customer routers go into the VRFs as regular routes. They get sent into BGP as VPN v4 addresses, because we're adding the route distinguisher, but that is unique to MPBGP. The P routers are not aware of that those routes exist.
Okay,
right?
so this gray box represents the P router, and each of those boxes, so each one of those boxes will be VRF, VRF, and then the global routing table.
Right.
All in one physical device.
Correct. These
Okay.
are all functions. These are all functions of the PE router. It's not 3 separate physical devices. This is actually a virtual route, a virtual router.
The global.
And then we have the global routing table, which allows, well, the primary reason to have the global routing table is reachability, to get from one PE router to the other PE router. Does that make sense?
Okay. Yeah, and then are you going to go into how you would want one customer talking to another customer, how that routing would work?
I don't know that we'll get into the specifics of that,
Okay.
but it would be, we will talk about adding additional services, like maybe using a service provider service, like a telephony service or other services. But all that requires is an agreement to exchange routes, from one customer to the other. So the routes are already there. There just has to be an agreement that's going to allow us to exchange those routes from one customer to another. Just like we would exchange routes between a service provider and the customer as well. So there are instances where the customer is also participating in routing that the provider is providing. Maybe they've got some sort of AWS connectivity, or maybe they have some sort of service provider, software as a service, or some sort of telephony service, or a subscribed service that the provider wants to provide to the client. So the client's going to be participating in that VPN as well, right? We would basically establish that that's a separate VPN function. We'll get into that later. That will allow us to identify how customers can talk to other customers as well. You'll get an understanding of that.
Okay, good.
Okay.
Thanks.
So we know that in MPLS VPN, the provider edge router provides isolation, right, which we were just talking about, between the customers by using these virtual route forwarding instances. The prefixes get propagated to the other PE routers through MPBGP. And again, that's what I was saying in the last slide, is that the P routers are not even aware that those prefixes exist. The P routers are simply there to allow the PE routers to communicate to each other. And if the client is participating in some sort of secondary VPN that the provider is providing, then there might be some communication with the P routers and the customer in that case. But the prefixes themselves, the ones that we're getting from the client, those get propagated to other PE routers using MPBGP. We identified the problem with this in the previous slide, right? The problem is that customers might be using the same prefix functions. They might be using the same address space. They might be using the same prefixes. So those prefixes have to be unique somehow, right? If the customers have overlapping IP addressing, that's obviously going to be a problem for BGP unless I can come up with a way of uniquely identifying those routes. And we do that with a route distinguisher, all right? Now, the basic idea behind a route distinguisher is pretty simple. Every single customer that the service provider is servicing gets a unique ID to distinguish between the prefix A or prefix B that comes from each customer, even if those prefixes are the same, right? 10/8 from customer A, 10/8 from customer B. Well, I got to be able to identify the difference between those. To create this unique prefix, the route distinguisher that was assigned to the client gets combined with the IPv4 prefix. And just to be clear, guys, when I say prefix, I'm just mean a route, right? And the combination of that is called a VPN v4 address, okay? In order for MPBGP to carry or in order for us to be able to transport, I should say, those unique VPN v4 prefixes, we have to have a protocol that understands what a VPN v4 prefix is. And multi-protocol BGP or MPBGP is specifically designed for that function. I mean, it has other features and other functions built into it, but MPBGP is specifically designed to understand these VPN v4 prefixes. All right? Now, the route distinguisher itself is a unique 64-bit number. It is prepended to the 32-bit customer prefix that was learned by the CE router. Remember, we're just talking about routes, right? We know that routes, particularly in IPv4, are 32 bits in length. So we've got essentially now a unique prefix that's 96 bits long, right? And that is comprised of the combination of this 8 bytes of route distinguisher. Oops, sorry about that. This 8 bytes of route distinguisher followed by the IPv4 prefix. All right. There are two ways that we can represent, or two formats, I should say, that we can represent a route distinguisher in. The first is what we call ASN:NN, right? And since they don't have it on the slide here, let me just write this down. ASN:NN. Can't really see my colons there. There you go. ASN:NN. ASN, of course, autonomous system number. That represents the autonomous system number, and the NN represents whatever other number, right? And we'll see in detail over the next couple of slides how these get represented in databases and so on. The second format, which is actually less widely used, is just to have an IP address followed by the number, NN, that's chosen. So this first format, this first representation, ASN followed by this number, is more commonly used. All right? It's not that complicated, right? The ASN represents essentially the route distinguisher, right? The customer information. So they do have it kind of listed here. This is the first format, and then this would be the second format. Now, the number itself is not the prefix, right? We're just talking about the format of the route distinguisher itself. And these are numbers or values that would typically just be provided by the service provider. I'm not completely versed or understand completely how the service provider chooses those numbers. I'm sure that there is a method that they use to choose these particular values. But the customer doesn't really have a choice as to what those numbers are. It's something that's chosen by the service provider to create this 64-bit unique identifier. Okay? And you'll see it represented typically as an ASN followed by a VPN identifier or the NN value. So this would be the NN value. This would be the ASN value. All right? That would be the NN value. All right? And like I said, we'll see how these numbers are represented a little. Well, actually, we kind of start to see a representation of it on the next slide here, right? In this diagram, the PE router receives the same prefix from two different customers, 172.16.00/24 from customer 1 and 172.16.00/24 from customer 2. Now, as long as those routes are unique in their own VRF, no problem. But the problem is those routes need to be exchanged between the BGP routers across the service provider network. So the routes themselves, the prefixes, get installed into the VRF routing table for each customer. When I have to propagate those two routes to the other PE routers, that's when we prepend the customer route distinguisher to create these unique VPN v4 routes. So when the other PE router receives those routes, they can identify what VRF those routes belong to. They can then strip off those route distinguishers and then install the actual routes themselves, the prefixes themselves, into the customer-specific VRF routing table for each customer. And then the rest is history, right? Because then the PE router simply exchanges those IPv4 prefixes with the CE router on the other side. So it's that route distinguisher that we see listed here. It's that route distinguisher that's going to allow us to uniquely identify each of those customer routes between the PE routers. Seems pretty simple, right? I mean, kind of makes logical sense. All right. All right. Now, another concept, and this is what I was referring to, Aaron, when I was talking about the client participating in multiple VPN networks, right? Whether it's, exchanging routes with another VPN client that's being serviced by the provider, or whether it's participating in some sort of VPN service that the provider's providing, like a telephony service or maybe a hosted firewall solution for internet access or whatever it might be. There has to be a way of participating in multiple VPN sessions, not just customer site to customer site VPN sessions. All right? And that's what we're going to talk about here. If the only thing that I had available to me was a route distinguisher to distinguish between routes and where those routes exist and where they're supposed to be populated and whatnot, it would be very difficult to achieve kind of a more complex VPN scenario where I want to participate in more than one VPN. So if you consider that, and this often happens, by the way, if you consider that a client may want to participate in more than one VPN, we have to initiate a secondary function within MPLS. We call these route targets, or RTs, okay? And the specific purpose of a route target is to allow the client to participate in more than one VPN scenario. If the only goal is to exchange routes from site A to site B within the same customer's network, then this option is not necessary. We don't need route targets to do that. But if the client wants to participate in multiple VPNs, including, Aaron, exchanging routing information or communicating to other VPN clients that the provider's providing service for, we have to have a route target. Think of a route target as a BGP extended community, basically. It allows the identification of VPN membership of particular routes, right? In fact, we actually use BGP communities to implement route targets. There is a 16-bit value, and it's the higher order 16 bits of the BGP extended community attribute. Remember that we didn't talk about this yet. We're going to get into BGP later on, but within a BGP extended community attribute, it's a 64-bit field, okay? the higher order 16 bits of that BGP extended community field is the route target. All right? And think of those higher order 16 bits as an encoded value that corresponds to the VPN membership of the specific site. All right? On the next slide, we'll actually see a visual representation of this, which will hopefully kind of clear things up. It's kind of hard to visualize without seeing a diagram, but we'll see that on the next slide. The route targets themselves get attached to the customer's route at the moment the PE router converts that route from a V4 route to a VPN V4 route. So let's say, for example, my goal is to exchange routing information from customer site A to customer site B. But, and I don't need a route target to do that necessarily, but if the customer is also participating in a secondary VPN or a tertiary VPN, then we need those route targets. So the route target gets attached to the route, and this is called an export route target, by the way. You'll see that on the test. The route target gets attached to the route as an export route target, and those are configured separately for each virtual routing table on the PE router. Again, it's difficult to visualize, so we'll see a picture of this in the next slide. Okay? The goal of this export route target is to identify a set of VPNs that the sites are associated with and the virtual routing table that it belongs to. All right? When the VPN v4 routes get propagated to other PE routers, those routers need to select the routes that are going to get imported into their virtual routing tables. Well, guess what? That importation, the importing of those routes and that selection is completely based on import route targets. Remember, the whole point of this process is reachability, right? I can export routes into a VRF, which then can later be imported into another VRF that allows reachability and connectivity. All right? And what routes we export and what routes we import depends on what kind of reachability I'm trying to achieve. All right? So you have to kind of think of it from that perspective. All right? And again, we'll see a visual representation of this a little bit later on. Each virtual routing table in our PE router can have a whole bunch of configured import RTs. It's just, again, a matter of what I want that site or that customer to be able to access. All right? We identify the set of VPNs from which the virtual routing table is accepting routes through the configuration. Let's take a look at a diagram, and hopefully that will kind of help clear things up a little bit here with regard to all the terms that we're using and the operation of route targets in this implementation. When the PE router receives a VPN v4 route, okay, and we can see we've got a VRF for customer 1, we've got import 1:1, import 1:100, export 1:1, and so on. So these are routes that are going into that virtual, either being imported into the VRF from the customer side, or they're being exported from the VRF to the other customer side, okay? So when this PE router receives the VPN v4 routes, it checks the export route target that's attached to that particular route. That route target gets compared to the import route target that is configured on all of the VRFs. All right. Now the point here is to ensure that is to identify what routes are going to get exchanged to the other PE routers, right? So I might have a PE router up here that is servicing, some sort of VPN function. In this case, it is the VRF routing table for customer 1. I might have another PE router here that's providing a VRF routing table for customer 1 and 2 if customer 1 and 2 want to talk to each other, and another one here specifically for customer 2. And it doesn't even have to be customer 1 and 2 talking to each other. In this case, it could be the customer talking to a VPN that the service provider is providing service for, right? But this scenario that you're seeing here, Aaron, is specifically what you were asking about, right? You were saying, what if I want customer 1 to be able to talk to customer 2? And that's...
Yeah, I was curious to know how they talk or communicate between VRFs.
Right. Well, they use these route targets, right? We have import and export route targets. Okay. So I'm guessing that other PE to the right has like an export 1.100, RD for 1.100? Yes.
Okay.
Yes. And by the way, there's not like 6 or 7 routers here. This is all one router, right? This is a PE router, well, virtually. I mean, this is the physical router, right? And these are all virtual instances within this physical router. They're just different VRFs, right? They drew it logically separate to give you an idea that we have this virtual separation, but it's still the same PE router, same physical PE router.
Okay, yeah, that cloud makes it look like they're at different geographic locations.
No, not in this case.
Okay.
Okay. So in this example, all right, and I'm going to try and break this down a little bit slower, with a little bit more detail, so that you guys can kind of follow along with what's going on here. But in this particular example, the PE router is injecting routes that are received with a route target of 1:1 into the VRF routing table for customer 1. So we're sending those VPN v4 routes with a route target of 1:1 into the VRF for customer 1. And we see that referenced as import 1:1. Okay? The routes with a route target of 1:2 get injected into the VRF for customer 2. We see that listed here as an import of 1:2. All right? The PE router is injecting routes with a route target of 1:100 into both routing tables, since both accept the route target of 1:100. And we can see that listed here as import 1:100, import 1:100. Now we can define what routes fall into that category. We may not want to exchange all routes from customer 1 to customer 2 and vice versa. Maybe it's only a couple of routes or a specific number of routes that are being exchanged. All right? So we have essentially a VRF routing table for the 1:100, which includes, well, those are the routes for customer 1 and customer 2. We have a VRF routing table for customer 1. We have a VRF routing table for customer 2. All right? Does that make sense? So the export that we see here for 1:1 here and the export for 1:2, that is for the normal exchange of routes between customer sites, which we don't see that in this topology diagram, but remember, we still have to be able to allow customer 2 to exchange routes with other customer 2 sites and customer 1 to exchange routes with other customer 1 sites. The downside to this particular class, and it's unfortunate, although I can understand you can't do everything in 5 days or 4 days or whatever it might be. But the downside is that you get a high-level view of this, but you don't get to really see the specific configuration, right? There's a CCNP service provider class that goes into the configuration of all of these components and so on.
So speaking of configuration, a quick question. So if you go to that PE router, you do like a show VRF route or whatever command you use. And if the routes happen to be overlapping, do those overlapping routes show up in the VRF table with some kind of identifier at the end of it or at the beginning, or how does that look?
At the beginning. They're going to have their route distinguisher. Well, the MPBGP routing table is what's going to have the VPN feed 4 routes. The individual VRF routing tables are just going to have the V4 prefixes. Does that make sense?
So okay, yeah, got it.
When you're looking at the individual VRFs, they're going to just look like regular routing tables. But when you look at the MPBGP routing information, it's going to have the VPN v4 routing information. Does that make sense?
Yeah.
All right. So you have a general idea of what a route target is. Again, we don't get to see the specific configurations because that's part of another class, but at least you have an understanding of at a high level of how these routes are exchanged between different clients or different VPNs, essentially. That's ultimately what it boils down to. They're just separate VPNs. Okay. Now, one of the other moving parts to this is the need or the requirement to exchange routes from the CE router to the PE router. All right. And this is probably the simplest aspect of MPLS that can be discussed because it's really just basically some sort of IGP routing process, right? It can be BGP. In a lot of cases, it is actually BGP, but it doesn't necessarily have to be BGP, all right? EIGRP can be used as a PE to CE protocol, and we'll talk in this slide about what the implications of that is. But when we are deploying EIGRP as the PE to CE routing protocol, we have to understand how EIGRP behaves and how a layer 3 MPLS VPN environment works with EIGRP in this case. You're going to find that it's pretty much the same as if it's just regular EIGRP because, again, we're not transporting EIGRP across the MPLS core. We're just using it simply to get the routes from the customer edge router to the provider edge router. So there is a process of redistribution that has to take place, right? Redistributing the routes from BGP into EIGRP makes all of those routes external, right? Because whenever I redistribute into EIGRP, the AD of those routes changes to 170. They become DEX routes. That also means, though, that some of the information gets lost during that redistribution process. And that situation can cause some problems when we have what we call backdoor links between sites. And we're going to see a visual representation of this in a little bit here. All right. To alleviate this particular problem, and we'll get into that we'll get into the discussion of a backdoor link and this backdoor problem as we move through the chapter here. But to alleviate this particular problem, there are extended BGP communities that are used in BGP to enable the remote PE routers to reconstruct those EIGRP routes with all of their characteristics. Right? Now, what kind of characteristics are we talking about? Metric components, right? Because we know that BGP doesn't handle metrics the same way that EIGRP does, right? In fact, it doesn't really use metrics at all. The autonomous system number information, route tags, the remote autonomous system number information, if we have a different remote autonomous system, remote IDs, remote metrics, just all of the characteristics that I would want to maintain in the EIGRP domain that would get lost if we just simply did, without community attributes and extended community configurations, we would lose all that information if we were doing redistribution from EIGRP into BGP and then back from BGP into EIGRP. Remember, we're talking about the process of getting the routes from one provider edge router to the other provider edge router. We know that there has to be some sort of redistribution for that to take place because we're going from some IGP protocol, which gets the routes from the CE router to the PE router, to our MPBGP protocol, which gets the routes from our PE router to our PE router. Okay? Even though it's not listed on the slide here, I can give you an idea of the extended community attributes that get appended to BGP routes to carry EIGRP information across the backbone. There are 6 of them, all right? One would be a route flag or a route tag, and that is used generally just to identify general route information, okay? Another value that might need to be propagated or carried over is something called the autonomous system or delay values. This is route metric information, autonomous system information, and so on. So that's going to be another extended community attribute or BGP community attribute that can be carried over. Other metric values, reliability, next hop, bandwidth, those are going to be carried over. Reserve, load, MTU, that's also used for route metric information. That's going to be carried over. Remote autonomous system number, remote ID, and then remote protocol and remote metrics. So those are the ones that that we can. That's the information that we can maintain by carrying this information over the with these BGP extended community attributes. All right. You guys understand generally what I'm talking about here, right? Information that BGP doesn't necessarily care about, EIGRP does care about. And we need to be able to transport that information almost as like a TLV value, although it's not, but kind of like a TLV, where we're just carrying vendor-specific information across BGP. This diagram here kind of represents what we just talked about, right? There are obviously multiple possible scenarios where we might implement EIGRP as our PE to CE routing protocol. Although in my experience, it's kind of rare. The provider doesn't generally like to use a proprietary protocol for the PE to CE communication. It can happen, right? I mean, it just depends on the service provider. So what we're seeing in this diagram is the enterprise is running EIGRP for their sites. We can see AS1 on this side here and AS2 on this side. So I am running multiple EIGRP autonomous systems. Because this is a layer 3 MPLS VPN, we can do that, right? Because we're essentially joining two autonomous systems, two disparate autonomous systems together over a routed domain, all right? So what happens is that the CE router advertises its network information via EIGRP to the PE router. So in this case, we've even decided to kind of extend our EIGRP domain directly to the PE router. Instead of running redistribution at this point and running some sort of IGP here and a separate IGP here. Again, not very common, but it doesn't really matter in this case because it could be that we're running EIGRP internally, maybe ASN3 here, and we're running ASN1 here, and we're just doing redistribution between those two EIGRP autonomous systems. But anyway, we are running EIGRP between the CE router and the PE router, okay? The PE router, of course, has to redistribute those routes from EIGRP into MPBGP, and that happens on the router itself. But we need to maintain that encoded route information in those extended community attributes within the MPBGP configuration. So assuming that those attributes are carried over, those attributes get distributed to the other PE router through MPBGP. So the PE2 router receives the MPBGP update, which includes these extended community attributes or this extended community information for EIGRP, as well as whatever the external matching EIGRP AS is, right? And in this case, it's AS2, or Autonomous System Number 2. Now, here's where the attributes come into play, because the PE2 router needs to recreate these EIGRP routes and send those EIGRP routes to the CE2 router. So I have to be able to exchange, I have to be able to exchange that routing information to that router. The routes have the same route type as the original routes, so they could be DEX routes or D routes. They have the same metric that the PE1 router received, and in that regard, the backbone is transparent, right? Because we maintain those attributes as part of a BGP extended community, the backbone didn't inject itself into the metrics, it didn't inject itself into the routing information. Does that make sense? So we call that a zero-cost backbone, meaning that the backbone appears from the customer edge side to be a zero-cost backbone, meaning it's not injecting additional cost into the routing path. All right. Again, we don't see how those attributes are carried. We don't see the actual physical configuration, but that's not really the goal here of this particular class. This is not an implementation class. This is a design class. So we're talking about the concepts, right? All right. Now, if I'm using EIGRP as the PE to CE routing protocol, kind of the same thing occurs, right? It looks very similar to what we saw on the previous slide, right? We've got this step 1, step 2, step 3, step 4. We went through those different steps. But now we're kind of looking at a scenario where we're running multiple autonomous systems. In the previous scenario, we were running multiple autonomous systems, but let's take a look at what happens if some sites are not running, say, EIGRP. Maybe I have a site running OSPF instead, okay? I'm not sure that, let me see, check something here. Yeah. That's strange. I think the diagram is actually incorrect because let me see what they're trying to say here. Yeah, okay. So it is correct. I was looking at CE2. We're running EIGRP at customer site 2, but in customer site 1, we are running OSPF. And that's perfectly fine. Because remember, we're transporting this routing information using BGP. So whatever we're running locally is kind of irrelevant, right? Except the routes that are being injected from the OSPF side have to be recreated as EIGRP routes on the CE2 router. All right? So we're running EIGRP at the CE2 site, but we're running OSPF at the CE1 site. The CE1 router is advertising the networks that it has via OSPF to the PE router here. Okay? The PE1 router redistributes the routes from OSPF into MPBGP. And again, we can encode routing information into the extended community attributes within MPBGP. We use MPBGP to exchange the routes with the PE2 router. So we're going to receive the MPBGP update from the PE1 router. But in this particular case, it doesn't include any extended community information for EIGRP because there wasn't any, right? We started with OSPF, so there isn't any extended community information for EIGRP. So what's going to happen in this case is that instead of creating these routes as D routes, right? On the previous slide here, we saw we're running EIGRP. So even though routes are being redistributed here from EIGRP into BGP, normally those would be DEX routes, but I can maintain in the BGP extended community attribute information, I can maintain those routes as D routes because I can set the attribute for type to a D route. So when the routes show up on this router, they still show up as internal EIGRP routes. We don't have that ability here because the attribute didn't exist, right? So when the PE2 router recreates the routes, they're going to recreate them as external EIGRP routes using whatever default metric is being advertised into the CE2 router. All right? So in the case, in this particular case, the originated protocol appears to be BGP. Doesn't appear to be OSPF because we weren't even aware that OSPF routes were being used on the CE1 side. We simply redistributed these routes from BGP into EIGRP. So they're going to show up with a DEX type, right? EIGRP external with an administrative distance of 170. All right? It's not a big deal. It's just important to understand that that's a possibility. All right? Very important to understand that that's a possibility. Now, I mentioned something previously called a backdoor link. And we didn't really talk about what a backdoor link was, so I want to kind of talk about that a little bit. It's a very simple concept, right? And we can see it's kind of depicted here. CE1 and CE2 are talking to each other over MPLS VPN, but they're also talking to each other directly. All right? You might think, well, why would I want to do that? Okay? Let's talk about that. So we have CE routers that are connected with this backdoor link, and the backdoor link is primarily used as a backup if for some reason the MPLS network fails or reachability to the MPLS provider fails or whatever. So the CE1 router is running EIGRP between the CE1 and PE1 router, and then between and also between CE1 and CE2. How could that be actually done? What might we be using to provide that service? Could be GRE with IPsec. It could be some other service provider VPN solution. Could be some sort of point-to-point connection, although probably not generally going to happen. If I'm running a point-to-point connection, I'm probably not needing MPLS VPN, but you know, it's some sort of communication directly between CE1 and CE2. When CE1 advertises route prefix, it's getting advertised to the PE1 router and the CE2 router simultaneously. We know that the PE1 router is going to install that route into its VRF, and then it's going to redistribute that EIGRP route into BGP. We're going to pass that route to the PE2 router using MPBGP and so on. The CE2 router is going to advertise that route, advertise routes to the PE2 router, and the PE2 router has 2 BGP paths for that particular prefix. It has the iBGP advertisement from the PE1 router. Remember, that's our MPBGP connection. And then it has a locally redistributed BGP route from the CE2 router EIGRP advertisement. In other words, we know that we can reach that prefix destination through 2 different paths. We can reach it through the MPLS network, or we can reach it through the backdoor link. All right? There is a problem with this, though. There is a BGP best path decision process that takes place, and locally originated routes are preferred with BGP. Now, what does that mean from this perspective? What kind of problem are we going to see from that? Anybody? Well,
it's going to choose this path, so basically it's going to prepare this path over the regular path.
Right. The decision means that we're going to forward over the backdoor link as the primary path. We don't want that to happen, right? That's not what the purpose of the backdoor link is. All right? There is an additional attribute that is known in BGP. It's called the BGP cost community attribute. And the BGP cost community attribute was specifically developed to handle this particular scenario. It is an attribute that we configure on the PE router. It attaches something called an extended community attribute. And what happens is the router looks at the cost community value, and it compares that value, and then that is what's going to influence what path I'm going to use for the routing process. All right? And simply stated, we adjust that value to influence which path the traffic is going to use. And of course, we want to make sure it uses the correct path. By default, when the PE router redistributes, when this PE router here or PE router here redistributes the EIGRP path into BGP, that BGP cost community attribute gets populated with whatever EIGRP metric exists on that particular prefix. We know that PE2 has 2 options. The iBGP path it learned from PE1, so through this path here, or the locally originated BGP path that was learned through the redistribution of the same prefix from the CE2 router. All right? Now, because we're adding the cost of traversing the backdoor link in this case, and that is that BGP cost community attribute, because we're adding the cost of this backdoor link now, the BGP cost community attribute, or, well, the BGP cost community of the iBGP path is lower. So that's going to be preferred and installed. Does that make sense? So this path would be the path that gets used. Sorry, let me clear that off. That path is going to end up being the path that gets used because because of the BGP cross community attribute being added to the backdoor link. All right. Again, we don't get to really see the configuration of this, but at least you're aware that this option exists and this feature exists. Okay. All right. OSPF. We know that that OSPF can be used as the PE to CE routing protocol. We saw that on the previous example, right, where we were looking at using OSPF on one side of the link and then using EIGRP on the other side of the link. But there are some things that we need to consider, just like we did with EIGRP and how EIGRP treats attributes and metrics and route types and whatnot. There are some things that we have to consider with OSPF as well. When we're deploying OSPF as our PE to CE routing protocol, there are certain types of behaviors that OSPF inherits as part of the process of communicating from the PE router to the other PE router and then doing the redistribution and so on. To propagate customer routes, from the PE router to the PE router, we know that those OSPF routes have to be redistributed into MPBGP and have to be redistributed again outside of MPBGP on the other PE router. The downside to this is that for all of those OSPF routes, they end up becoming external routes on the remote PE router when they get redistributed back into OSPF. We know that the administrative distance doesn't necessarily change because the administrative distance of all OSPF routes is 110, but the type changes. We go from an O route to an OE1 or OE2 route, all right? And by the way, those external routes, that redistribution process makes those external routes less preferable than again, routes that might be learned through a backdoor link or some other process. We know that internal OSPF routes are advertised as summary routes, right? If they're going from one area to another. If they're going from the same area to the same area, then obviously that's going to be an O route or a type 1 route. But usually we're connecting multiple areas through our MPLS backbone, so those internal OSPF routes are going to get advertised as type 3 LSAs or summary routes on the PE router. And then when they're redistributed back from BGP into OSPF, they'll show up as those type 3 routes. We can kind of see that in this particular case. We've got area 0 connected here. We've got type 1s, type 2s, type 3s because we've got area 1 here. So we know on this ABR that we're going to see type 3s coming back and forth here. Type 1s and 2s would exist inside this area. Remember, type 1 LSAs are generated by every single OSPF router. Type 2 LSAs are generated by DRs and BDRs. We've got our VPN v4 routes because we're adding the route distinguishers to the routes as they go through the MPLS network. So we have area 0 kind of extended across the MPLS backbone, which is possible. You can do that because remember we're creating this VPN, this virtually private network. All right. So we've got type 3 routes that are going to come into this area, type 3 routes that are going to come into this area. Because those internal routes are advertised as summary routes, when they're redistributed back from BGP into OSPF, this is going to prevent all redistributed routes from becoming OSPF external routes. They're going to become inter-area routes, the type 3 routes. That's actually different than normal behavior, if you think about it, because the PE routers are performing redistribution. We normally would see those generate type 5 routes, right? OSPF external routes. But the PE routers are actually acting as ABRs instead of ASBRs. It's kind of counterintuitive, right? You think of redistribution, you always think of ASBR because that's what an ASBR does. It redistributes routes from one autonomous system into another type of autonomous system. But that's not the way it works for MPLS VPNs. The PE routers are actually acting as area border routers, not as autonomous system boundary routers. Okay? That means that all OSPF internal routes become inter-area routes. That may not be something we want to happen, right? I don't want those type 1 routes to become type 3 routes. And by the way, that would be true even if the area number matches on the different PE routers. They still become type 3 routes. It's a very, very strange scenario. You wouldn't expect it to look that way, but it does. Okay? Now, obviously, there are ways that we can handle that. We can use BGP extension kind of excuse me. The PE router is, well, it's actually able to reconstruct the OSPF route, just like we talked about with EIGRP using these BGP extended community attributes. The PE router is able to reconstruct the OSPF route with OSPF specific parameters that are carried in the BGP extended communities. Things like the route type, which indicates what kind of route the PE router should advertise into OSPF, right? Is it going to be an inter-area route, type 3 LSA? Is it going to be a type 1, type 2, et cetera, et cetera? The domain ID, that's going to allow us to indicate the remote PE, to that remote PE router, how to advertise external OSPF routes, right? Is it going to be a type 1 or a type 2 external route? By the way, the default domain ID is the same as the process ID for OSPF. If the domain ID of the received route is different from the OSPF process in the VRF, then we advertise the route as an external route type 2. I'm not talking about LSA type 2, I'm talking about OE2, right? We know that external routes are type 5s, unless we're using special area types, and they can be type 7s, but additionally, external routes can be considered as an external type 1 or as an external type 2 route, all right? I guess the bottom line here is that in order to maintain or to ensure that we're keeping that information that gets lost through the redistribution process, we have to use those BGP extended community attributes, and we have to set those values in the BGP configuration, all right? If we want to preserve things like the metric, the PE router is going to use the OSPF metric to set an attribute in BGP called the multi-exit discriminator value, or the MED attribute. So when that route gets redistributed again into OSPF on the remote PE side, we're going to use that MED to set the actual seed metric for OSPF of the internal or external route that's being sent into OSPF, again, from the PE router. Make sense? This is the challenge that we have when we're dealing with these Layer 3 MPLS VPNs. None of this exists with Layer 2, because in Layer 2, the service provider is not actually participating in the routing. But with a Layer 3 MPLS VPN, these are considerations that we have to take into account. All right. Now, we know that OSPF uses a hierarchical structure, area design to facilitate scalability and efficiencies in the OSPF design. And OSPF uses areas to actually create that network hierarchy. Area 0 is the backbone area, and that's going to allow us to connect all of our other areas. The MPLS VPN backbone can kind of be considered as an additional layer of hierarchy that is actually higher than the backbone area itself. We actually have a term that we use to define that. We call it the MPLS VPN super backbone, right? That may be a term that you guys may have heard of in the past. It's not actually an area itself because it's not running OSPF, it's running IBGP. But it acts as an area, and the PE routers themselves act as ABRs to that area, since by default, those PE routers are going to advertise type 3 LSAs to the CE routers. So it's an interesting concept because you don't necessarily usually think of the MPLS VPN backbone acting as an area, but in this case, it actually is. The CE routers themselves, they can be in area 0 if you want them to be in area 0, or they can be in any other area that you want them to be in. If we have more than one area at the customer site, the PE router has to be in area 0 because it's acting as an ABR. And then you have to set up a virtual link between the PE router and the nearest ABR in the customer site to bring area 0 up to that PE router. All right, so what you're looking at in the diagram is kind of the different deployment scenarios, right? Area 0 is on the PE routers, and then we're connecting area 1 using that MPLS VPN backbone. That's the first scenario that we see here, right? The second scenario, we have a non-zero area on the PE routers. In this case, it would be area 1, so we don't really have an area 0 at all, which is perfectly fine as long as you're not running any other areas, all right? We can see in the case of the third diagram here, we have a area 0 on the left, we have area 0 on the right, but it is discontiguous. So we have to set up a virtual link on the PE router and the CE router so that we can attach that discontiguous area 0 to the MPLS backbone, okay? And then we can also extend area 0 across the MPLS VPN using that non-zero area to area 0 on each side of the PE routers. So these are kind of the different deployment scenarios that you might see. Most common would be either the top 2 or the bottom one. And the third one down would be typically temporary, right? As we're kind of migrating from one area to another, or redesigning our OSPF backbone. All right. In normal OSPF operation, intra-area routes are more preferred than inter-area routes, right? I'm always going to prefer a type 1 route over a type 3 route. We know that from just our basic knowledge of OSPF. In MPLS VPNs, all internal OSPF routes become inter-area routes at the remote site. Remember, those PE routers are acting as ABRs. Even if we have the scenario here where we have, the same area on both sides, we still see those routes as inter-area route or inter-area routes as opposed to intra-area routes. If we have a backdoor link between the sites, this can cause a problem, right? Because now all the intra-area routes remain intra-area routes across the backdoor link. So those intra-area routes that get advertised across the backdoor link are always going to be preferred routes over the inter-area routes that I might get from my PE routers being redistributed. All right? Now, in the case of OSPF, we don't solve this problem by changing the route types because we can't actually do that in OSPF. The PE router is always going to act as a ABR. So we can't really trick the PE routers into redistributing those routes as type 1 routes. So what we have to do is we have to create this special link between the PE routers called a sham link. And you can see it depicted on the diagram here. All right? A sham link is basically just a fake link between the PE routers. I don't know if you guys have ever had experience configuring these in the past, but it has two endpoints, right? Each endpoint has a /32 prefix, and then that IP address that's on that endpoint has to be in the VRF routing table for the customer. And then IBGP has to advertise that IP address from one PE router to the other PE router. All right. The sham link is essentially, it's just a point-to-point link between those two /32 host addresses. All right. It's part of the shortest path first computation, just like any other link in OSPF. And the LSAs get flooded across the sham link. But here's the thing. The OSPF route types get preserved, and they're not converted to type 3s or type 5s across that link. Now, if that sham link fails for whatever reason, we can still route. Routing is still possible, but then we revert back to inter-area routes, and again, the backdoor routes would take preference in that case because they're intra-area type 1 routes as opposed to inter-area type 3 routes. Does that make sense? All right. Now, even if the sham link exists and the OSPF routes get flooded across that sham link, BGP still advertises the OSPF routes as VPN v4 routes from the PE router to the PE router. Right? That has to happen, right? It has to happen because BGP still has to carry those MPLS VPN labels so that we can forward the traffic across the MPLS VPN backbone. Again, we don't see the specific configuration of a sham link in this case, but you understand that it exists, of course, and what the purpose of that sham link is. If we have time, and I'm hoping that we'll be able to make some time even if we dock off a couple of lessons, but if we have time, I'll try to demonstrate some of these configurations as in GNS3 we'll put together some little topologies and try and demonstrate some of these concepts. Okay? MPBGP can even be used as a PE to CE routing protocol. And quite honestly, in my experience, this is generally the preferred protocol. It's actually really one of the most common methods of communicating from your CE to your PE devices. I don't know if there's a specific reason. I would imagine that it's one of the primary reasons is that BGP is what the service providers understand. It's the protocol of choice It's how we transport data across the MPLS VPN core. So naturally, it's a protocol that the service provider engineers understand. Now, there's obviously probably some technical reasons as well, but in my experience in dealing with our clients and our customers, BGP would be that PE to CE protocol. Once I've decided to use MPBGP as my PE to CE protocol, we have to identify how we're going to allocate our autonomous system numbers. If we are using MPBGP AS numbers for enterprise sites, it's a very important consideration because it affects how the network behaves, right? Things like load balancing, route loop avoidance, site characterization over the origin autonomous system number. Remember, BGP is a path vector protocol. It uses BGP path attributes to make routing decisions. So the autonomous system number can play into that heavily. In fact, that is the very first attribute that we actually consider by default, right? We have weight and we have local preference, but we also have the AS path attribute because weight and local preference are usually defaulted to their default values, okay? Now, if we choose to use MPBGP as our PE to CE protocol, we have two options for autonomous system allocation. We can simply use the same autonomous system number for all customer sites, or we can have a unique MPBGP AS for each customer site. There is an advantage to actually allocating a unique autonomous system per site, and it's one of the reasons why we tend to do this in our deployments, is that by having a unique autonomous system per site, we can actually identify the originator of the route based on that autonomous system number, right? All we have to do is check the AS path attribute for the origin of that MPBGP autonomous system number, all right? Kind of makes it easier to troubleshoot. That unique autonomous system number per site allows us to create AS path filtering, to perform BGP route manipulation, and so on. So if I use a common autonomous system number across all the sites, I lose some of that functionality that I would have if I have a unique autonomous system number for each site. And remember, these autonomous system numbers don't have to be public, right? In fact, they're usually not public. They're just simply private ASNs that we pick from the private range, right? Because we get all of those, all that functionality, the ability to apply filtering, to be able to identify the origin of the route based on AS path, the unique AS approach is really the preferred approach in implementing autonomous system numbers at each site. Now, there is an advantage for using the same AS on every site. There is something within BGP called an AS collision. And this, obviously, having the same autonomous system number for every site reduces the chance of having those autonomous system number or AS autonomous system collisions. There is a level of complexity, though, that gets introduced, and the extent of my knowledge on this particular aspect is really limited to what I've seen in a lab environment, because like I said, the most common approach is to use a unique autonomous system number for each customer site. So there is some complexity that gets introduced if you have the same autonomous system number for every single customer site. MPBGP peers, when they're routing, or when they're making their path selection or choosing a path, they perform something called AS loop prevention. All right? And they do that by verifying that the AS path attribute in the received update contains its own autonomous system number. All right? If for some reason a route that's being received, which has an AS path attribute tied to it, that's one of the mandatory attributes in BGP, a route that has this, the local AS number or ASN in the route, that route typically gets discarded, right? Because the CE router on the other site sees its own autonomous system number as part of the AS path attribute, which means that that could be potentially a routing loop, right? Even though BGP is generally classified as a path vector routing protocol, it's fundamentally a distance vector protocol. I mean, it uses a lot of the same loop avoidance mechanisms that distance vector protocols tend to use. All right? So if we want to use the same AS number for every customer site, we have to disable that AS loop prevention technique. The service provider will actually use something called AS override to perform that particular task. All right? And when the service provider uses that command, it replaces the customer autonomous system number with its own AS path its own AS in the autonomous system number path attribute. When you use mechanisms like AS override, obviously that's going to increase the level of complexity, the configuration requirements, and so on for the service provider. There is another issue that arises too when you use the AS override, and that is that none of the MPBGP routes can be uniquely identified as originating from a specific site based on the AS path attribute, because the AS path attribute has been rewritten. And even if it wasn't rewritten, we would still see a common AS in each of the path attributes, because we're using the same autonomous system number across multiple sites. If the customer edge router wants to identify the origin of the route, it has to be based on some other attribute. We have to use another mechanism, maybe some sort of MPBGP standard community attribute or something to that effect. So that means we're going to have to configure our CE routers to support that additional feature, that additional option. Rewriting the AS path attribute prevents the CE router from detecting the MPBGP loop, because we obviously can no longer rely on that because we're overriding that feature. That's going to present problems if you have a multi-home site. All right. Now, there is a feature, it's called SSO, and, SOO, not SSO, but SOO, and that stands for Site of Origin. And that site of origin is an extended community attribute within BGP. It gets attached to the MPBGP route, and it's used to identify the origin of that particular route. If the site of origin is the same, then the route is blocked from being advertised. So it adds that kind of loop avoidance feature back into the configuration. Again, this would be something that would solve that problem that was created for multi-home sites as opposed to single-home sites. So it may not be something that you actually have to implement. But you can see, by using a common autonomous system number across multiple customer sites, you're introducing a whole lot of complexity into the design of your MPLS VPN solution, which is why most people will use unique ASNs. All right. If the customer has a backdoor link between the sites, and we kind of see that listed here, we've got our MPLS VPN, and then we have some sort of backdoor link between C1 and C2. When the customer has this backdoor link, the same route gets advertised over the backdoor link using whatever IGP that gets advertised over the MPLS VPN backbone. Because we need to redistribute routes from MPBGP into our IGP on the CE router, the routes that actually go over the MPLS VPN backbone become external routes. We saw this same problem when we were dealing with OSPF and how OSPF handled backdoor links as well. Inter-area routes versus intra-area routes and so on. We weren't necessarily dealing with external routes, but we had the concept of an inter-area route, which is a type 3, versus intra-area routes, which are type 1. The routes in this case become internal routes, right? Routes over that backdoor link become internal routes. And since an internal route is always preferred over some sort of external routes, the routers are going to use the backdoor link instead of the MPLS VPN backbone, which we don't want to happen, right? So we can solve this problem very simply in this case by summarizing routes over the backdoor link. That means that the routes over the MPLS backbone become more specific, and we know that routers choose longer prefix matches to route packets as opposed to shorter prefix matches. So kind of a simple solution, and it wouldn't apply to the OSPF problem that we saw previously, because type 1 routes, whether they're summary or not, are always preferred over type 3 routes, right? LSA type 3s versus LSA type 1s. So even if the type 3 was more specific, it still wouldn't be preferred over a type 1 route. But in this case, we're talking about BGP with some sort of IGP route, or external versus internal in this case. So the more specific routes would be more preferred. All right. So let's take a look at a case study. In this case study, we're going to establish connectivity between two sites. We're going to use a layer 3 MPLS VPN solution from our local service provider. We've got the 192.168.1.0 route in site A, and I've got the 192.168.2.0 route in site B, and I'm using OSPF to exchange those prefixes from the CE router to the PE router. Pretty basic configuration, pretty basic scenario here, all right? The OSPF is configured on the interface towards the PE router, and then the service provider is going to configure OSPF on their interface towards the CE router. So we're actually going to see an OSPF adjacency between the CE router and the PE router, and the 1.0/24 prefix is going to get injected into the VRF routing table on the PE router because it's being sent over by the CE router, okay? All right. So that's the general step 1. That's the basic layout. In step 2, the PE router needs to inject the prefix of 192.168.0/24 into the VRF routing table on the PE router itself. Now, the service provider has actually configured a route distinguisher for this particular customer. Even though we're not seeing other customers as part of this topology, let's assume that they exist. So we have to identify this customer uniquely, and in this case, we're doing that with an RD of 1:100. In addition, we have import and export route targets that are configured, and those import and export route targets are 1:10. And we've decided to use that same value on all of the PE routers. The diagram doesn't really show us the other VPNs that the client might be participating in. It doesn't show us the other VPNs that the service provider might be providing. But we're kind of incorporating all of these concepts that we've talked about over the last couple of hours into this case study. All right. All right. Step number 3. We have to, of course, prepend, or append, excuse me, sorry, not prepend, but append the values of the route distinguisher to the IPv4 prefix to create that VPN v4 address. In this case, it's going to be 1:100. We see it kind of in the middle right here. 1:100:192.168.1.0/24. We send that, the PE router sends that prefix across the MPLS backbone to the other PE router using MPBGP. And the PE router attaches the route target to the VPN v4 prefix as well. It's not actually appended to the route itself, the VPN v4 route, but it is attached to the attached to the route. So we know what VRF that route needs to be injected into. That's based on our import and our export route targets. And by the way, you did notice on the previous slide, you don't have to have unique, let me go back to the previous slide here, you don't have to have unique import and export route targets at each location. You would for each VPN, but not for a common VPN. We have a common VPN in this case that we're sharing routes between. All right, so we're using the same RT value. The value in this case is 1:10, and that's configured as the export route target on the PE router, as well as the import route target on the receiving PE router. When the PE router at the other side receives that VPN v4 prefix over MPBGP, it's going to strip off the route distinguisher tag. It's going to import the IPv4 prefix into the correct VRF routing table based on the import route target. Remember, the PE router uses that route target that it received with the prefix to choose the VRF that the route's going to go into. But when we're inserting the route into the VRF, we don't need the route distinguisher anymore, right? Because the VRF is unique to that customer. So that route distinguisher tag gets stripped off in the process. The route target on the received prefix was 1:10. That's what the export route target was on the previous, on the PE router on the left side. That's what the import route target is for the VRF on the right side. Think of it as just kind of like a tag, right? So I could say, for example, the import route target on this side is 1:10, and the export route target here would be 1:10. But on this side, I could say the export route target is 1:20, and the import route target here is 1:20. It's unidirectional, right? The reason it's the same is because it doesn't really matter. Whatever the routes are being exported as, any VRF that has that value identified as an import, that route goes into that VRF. Does that make sense? It's kind of like a little label that we apply to the routes to identify. And by the way, that route can be injected into multiple VRFs. It doesn't have to only go in to one VRF. I would have one export RT, possibly multiple export RTs, and I can have multiple import RTs per VRF. You have to make sure, of course, that you have unique routes for those imports and exports, because you don't want, conflicting routes coming from multiple sources. All right. Because the route target that was received on the prefix was 1:10, that was the export route target on the PE router on the customer side A. the PE router on site B checks the VRF to see if the import route target 110 exists. In this case, it does. And it's going to import that prefix into that VRF routing table. Okay. Aaron, this was a question that you had previously about how customers participate with each other. Does this help you understand how that might happen?
Yeah, it does.
Okay. You know, each customer would have its own unique export route target, and then I'd use whatever import route target to basically just put those routes into that VRF routing table. All right. Now on step 5, we have essentially agreed with the service provider to establish an OSPF connection from the PE router on the right side to the CE router at site B, just like we did on step 1 where we had the OSPF agreement between the CE router and the PE router for site A. So that means that the PE router at site B then forwards the 1.0/24 prefix to the CE router without a route target, without a route distinguisher, because that's all gone now. We're now into OSPF. And then the 1.0 prefix is in the routing table of the CE router. And now people from site B can actually access that particular prefix. This exact same process is repeated in the reverse direction. We want the 2.0 prefix to show up. Hi. We want the 2.0 prefix to show up in the site A router, right? So both prefixes are going to show up in the routing tables from site A to site B, and we're going to have full connectivity. Okay. Obviously, the point here is now we have full connectivity between the sites, and we can route back and forth. You know, there's a lot of stuff involved in MPLS, but I think hopefully by going through this lesson, you guys have a better picture of all of the different parts that are involved in getting routes from one site to the other and moving data back and forth. The one thing that we haven't talked about so far is where's MPLS? We haven't mentioned labels. We haven't mentioned label switching or attaching labels to data and moving it across the provider network. So that's the last thing we talk about. That's the last piece we talk about in this case. In order for us to forward traffic from one site to another, the packet itself has to go through the MPLS core. And that involves the use of the P routers and MPLS making those forwarding decisions. So MPLS is the core technology used in that forwarding process. All right. We'll use this diagram, and I'm going to describe to you, because it's just a diagram, right? So you don't get all the details here. But I'm going to describe to you the procedure that's used to get the packet across this MPLS core. All right. Now, the customer network originates the packet. We know that. And it's obviously a packet that's supposed to go to the other side. So the CE router sends the packet to the PE router, and all that stuff we've already kind of talked about, how that happens, and you know what happens with the labeling and everything else. The PE router receives the packet. It does a routing lookup according to the VRF routing table. We've already built routing tables. We've already gone through that whole process. Now we're actually just trying to transfer data, the routed packets as opposed to the routing packets, right? So the PE router receives the packet. It does a routing table lookup according to the VRF routing table. And at this point, we've now decided how we're going to route the packet. This is the first time that MPLS comes into play. The provider router, or the provider edge router, not the P router, but the provider edge router, imposes two labels on this packet. All right? That's a term that you'll see on the exam. That's a term that you need to know. We are imposing the labels, right? Attaching the labels, essentially. there are two labels. There's an outer label, and then there's an inner label. The first label, which is the inner label that gets imposed, is the VPN label. And it is the label that's used to uniquely identify the customer. In this particular case, it is the yellow label, right? This inner label here. Oops, sorry. This guy right here and this guy right here. And you notice that as the data passes through the MPLS core, that label doesn't change. That label stays the same, okay? That is called the VPN label, and its sole purpose is to uniquely identify the customer's VPN prefix. The second label, which is the outer label, is what we call the forwarding label. That would be the orange one and the purple one in the diagram here. All right, that's used to tunnel the packet through the provider's MPLS network. Okay, so that label is our switching label. That label is going to change from router to router, switch to switch in the network. The labeled packet is forwarded at each hop through the service provider core. So each P router, and this is where the P routers come into play, each P router makes a forwarding decision based on that top level label, not the VPN label, not the bottom label. Okay? The top level label is what gets swapped with a new label. The underlying packet and the inner label get left. They're never changed, never swapped, and they stay the same throughout the entire process. So why have the VPN label? What is the point of the VPN label if it's not used to move data across the MPLS provider core? Well, it's used at the other side. When the packet arrives at the remote PE router, the router looks at that inner VPN label and kind of uses that as a customer prefix. All right? So we do something called penultimate hop popping before we get to the PE router. And this diagram is not really drawn very well because we actually pull off that outer label before the data gets to the PE router. But that VPN label identifies the customer specifically. Now, the VPN label is no longer necessary, right? So that gets stripped off, and then we use we base our routing decision on the IPv4 packet based on the VRF routing table, right? The diagram, as I said, is not really drawn very well. The forwarding label is usually going to be removed at the P side, right? The last P router in the MPLS network removes that forwarding label, but they only have one P router here, so they should have had a couple of P routers. So I wouldn't necessarily see this label here at the PE router. That would have already been removed, and that process is called penultimate hop popping, okay? Penultimate means like the last step or whatever, and we're popping off that outer label on that process. Lastly, of course, the original IP packet then gets forwarded to the remote CE router, and we use our regular routing information to get that packet to its final destination. All right. Now, there are a couple of different, ways that MPLS VPNs can be implemented. There's VPLS, which is called Virtual Private LAN Service, or that's an acronym for Virtual Private LAN Service. And there's VPWS. VPWS is Virtual Private Wired Service. And you guys are definitely going to have to know the difference between VPLS, the LAN service, and the wired service as well. So we're going to wrap up this chapter by talking about the differences between VPLS and VPWS. What we're looking at first, though, is VPWS. VPWS is a basic solution for transporting layer 2 packets over an MPLS VPN backbone. All right? In that sense, the CE routers have a direct connection with each other. That's why it's called VPWS, because the MPLS provider network is a pseudo wire. It's a fake wire, right? It's basically a point-to-point circuit. So when we're dealing with VPWS, a lot of the things that we talked about previously don't exist anymore because the service provider is not participating in the routing of the customer's traffic. The routers themselves have a direct peering relationship using an IGP. All right? So this whole architecture is based on a concept called a pseudo wire. The pseudo wire itself carries the customer's layer 2 traffic from site to site over that MPLS network. It's a connection between the PE routers that emulates a wire that's carrying layer 2 frames. All right. Now, MPLS still exists, right? We're still doing labeling. We still have the VPN label to identify the client traffic, and we still have the switching label to allow us to switch the MPLS traffic across the MPLS core. But the layer 2 frames are the ones that are actually being encapsulated inside those MPLS labeled packets. All right. The end result here of VPWS is that the customer edge devices are directly connected over the provider's network. If I'm running, in any type of network that's running this VPWS solution, all of the routers in the service provider network run MPLS. The PE routers are connected to the CE routers just like before, but the PE routers receive layer 2 frames, and then they encapsulate them with the labels before sending them on to the destination towards the other PE routers. It's the remote PE router that removes the label and then sends that frame, not the packet, but the frame towards the remote CE router. All right? Just like we saw in the previous example, there are 2 labels when packets get forwarded over the network. The inner label is used to identify not the customer in this case, but the pseudo wire. The outer label is my switching label that allows me to forward that traffic from one side of the MPLS network to the other side. Okay? The nice thing about this particular solution is that we can transport anything over the MPLS network. It can be frame relay, it could be ATM, it could be PPP, it could be HDLC. In most cases, it's Ethernet, but because it's a layer 2 pseudo wire, we don't care what the protocol is, right? We simply transport data. Ethernet, of course, is the simplest, layer 2 encapsulation process that we can deal with. And it works very well in fully meshed or multi-homed environments as well, because we use ARP and MAC addresses and all that to facilitate the communication between our layer 3 devices. All right, so that is the wired service overview. Now, let's talk about some of the other options that we have with this VPWS function. And then lastly, we'll take a look at the VPWS design and see how the big picture of everything and how it all kind of fits together. We know that VPWS can carry Ethernet frames. And those frames get carried from PE router on the right to the PE router on the left and vice versa. this is literally, well, I guess not literally, not physically, but virtually a point-to-point connection between the PE routers. All right. So we use a protocol called EOMPLS, and we see that listed, here. EOMPLS. It stands for Ethernet over MPLS, or well, actually, a lot of people call it Ethernet over MPLS, but it's actually, some people like to call it everything over MPLS. But technically speaking, it's Ethernet over MPLS. All right. And the purpose of it, of course, is to transport Ethernet over our MPLS network. Okay. When we're doing that, though, there are two modes that we can operate in. All right. Now, this is all part of VPWS. This is not part of VPLS. So we're talking about kind of a subset of EOMPLS over VPWS. All right. Two different modes. We've got port mode and we've got VLAN mode. Okay. Whatever mode we decide to use, whether it's port mode or whether it's VLAN mode, determines how tags are applied, 802.1q tags, right, because this is Ethernet, how the tags are applied and processed over this pseudo wire. All right? So I'm going to describe the difference. I mean, they have a couple of bullet points on the slide here, but again, it's not really that detailed, so I'm going to kind of give you additional detail on this. If I'm operating in port mode, okay, what's going to happen is the data is going to get encapsulated and transmitted, but we're going to encapsulate and transmit the entire layer 2 frame that it receives on whatever ingress interface that I have. Now that's going to include the 802.1q header if I've got an 802.1q tag, and it's going to allow me to transport the entire frame, right? Port mode is entirely transparent, so it allows the customer to use this pseudo wire as a standard Ethernet link. So I can set up 802.1q trunking. I can use 802.1q to carry multiple VLANs across the pseudo wire and so on. All right? If I'm operating in VLAN mode, and by the way, port mode would be probably in most cases the preferred method, but if I'm operating in VLAN mode, the .1q header of the incoming frame gets examined to determine the circuit where the frame needs to be transmitted. So think of the VLAN tag almost like a DELC in frame relay, or a VPI or VCI in ATM, right? We might have multiple pseudo wires, and we're segregating or separating that VLAN traffic and using the 802.1q tag as the connection identifier. All right? Sorry about that, guys. So, do you guys have a general understanding? I mean, obviously, there's a little bit more I want to tell you about this VLAN mode, but port mode is kind of like setting up a trunk link between two different switches, and I can pass any VLAN over that single pseudo wire, and so it actually acts very much like a regular trunk. In VLAN mode, the .1q header identifies the circuit that the frame needs to be transmitted over, right? So on the egress, the .1q header is rewritten to the VLAN that identifies the circuit on the other side, right? This is completely analogous to the concept of virtual circuits in frame relay or ATM, which means I can kind of redirect traffic to different locations based on the VLAN tag to identify the circuit. So in this particular case, it's not transparent, right? The customer-defined VLANs are not transparently carried across the circuit. All right? Additionally, the EOMPLS VLAN mode requires that you have 802.1q VLAN tags present on the frame so that we can actually select the outbound circuit that's going to be used for that traffic. We cannot pass untagged traffic like we could in port mode. All right? You can actually mix and match these, by the way. You can define port mode on one end of a circuit and VLAN mode on the other side. This would be particularly useful if we're trying to implement like a hub and spoke architecture. At the hub site, thank you.
You're welcome.
At the hub site, the circuit is operated in VLAN mode to select the different VLANs to identify each of the spokes. And at the spoke side, the circuit is operated in port mode, so we don't necessarily have to have tagged frames for those particular packets leaving the spoke side. So the link between the spoke CE and the PE router uses a basic Ethernet frame, and the link between the hub, on the hub side, the link between the hub CE and PE uses .1q trunking to identify traffic and to identify what traffic goes to what spoke and so on. Does that make sense? So it gets even a little bit more complicated when you're dealing with the wired service versus LAN service. All right. Now, from a customer's point of view, the wired service offers a solution where devices see devices at remote sites as directly connected devices. We talked about that when we introduced this concept initially. The CE devices can be routers, they can be switches. It doesn't matter what they are because this is all layer 2 concepts. All right. When we connect a router to a VPWS, we have to deploy some sort of IGP routing protocol to forward the traffic between the sites because the network is essentially transparent to the CE routers. So the CE routers can form direct neighbor relationships, direct adjacencies. The entire MPLS service provider cloud is transparent. What's the advantage? Well, the advantage of this solution is that we gain complete control over the routing in the WAN, right? And we don't have to worry about the provider, participating in routing and carrying attributes across the BGP domain, et cetera, like we talked about with a layer 3 MPLS VPN. These are layer 2 MPLS VPNs. All right. So we don't have to have some sort of peering relationship with the service provider. We don't have to exchange routes with the service provider or nothing. All of the convergence and all the control is under the customer's control. All right. If we have multiple links to the WAN from CE routers, we can actually influence which link would be the primary link and which link would be the secondary link as well. So there are quite a few benefits to operating in this layer 2 mode. All right. All right. The PE operation mode in this particular case does affect the CE deployment. When the provider edge router is operating in port mode, we talked about what port mode was previously, all the traffic gets tunneled to the remote location. So the CE router needs to have an IP address on its physical interface, and it has to be in the same subnet as the physical interface of the remote device as well. We can use sub-interfaces if we want to, if we have multiple layer 3 connections at the remote site, just like you would if you connected 2 routers back to back and you had multiple subnets. You could do trunking or 802.1q tagging and have different subnets across the link. when we're connecting a remote site, we need to physically connect the extra link from the CE to the PE router at the hub site. This would be if we this would be if we had, you know, a hub and spoke type of deployment or a hub and spoke type of environment. There is a good option if you're primarily using this for a low number of point-to-point connections as well, right? Having separate sub-interfaces for each point-to-point connection. But if the PE router is operating in VLAN mode, right, and notice it's the PE router, not the CE router, that gets configured for the appropriate mode of operation. So this would definitely be something that you would have to identify in conjunction with the service provider. But if the PE router is operating in VLAN mode, we have to configure multiple sub-interfaces on the PE side, because each sub-interface then gets connected to a different remote site. If you remember, it's very much like a virtual circuit configuration in ATM or frame relay, where we have the 802.1q tag that allows us to identify what pseudo wire that the traffic is going to pass over as it goes over the MPLS network. All right. Each sub-interface then would represent kind of a different pseudo wire to connect to different remote sites. This is an ideal solution for like a hub and spoke environment. We talked about that. The spoke sides don't necessarily also have to be a VLAN mode operation. They can operate in port mode, but the hub side would definitely have to operate in VLAN mode so that you could identify each individual pseudo wire that would be tied to a different sub-interface on the CE router going to the PE router. We can use switches to connect the CE devices to our layer 2 network between the remote sites. And this is usually to provide some sort of layer 2 transport between data centers or a data center interconnect. And you have to have spanning tree enabled on the switches, so BPDUs are being passed back and forth to avoid switching loops, and all the other layer 2 concepts that we normally would deal with, we need to deal with in this type of environment. There are a couple of other considerations that you have to take into account when you're using VPWS. For example, supported MTU sizes, right? WAN support, quality of service support, and the transparency aspect. In a VPLS design, remember, VPLS is a virtual private LAN solution or service. All right. In a virtual private LAN service, we're emulating a LAN, a local area network communication across the MPLS backbone. It's a multi-point layer 2 connectivity, though, much like just a switch would be, right? Where you can have Site A, Site B, Site C, Site D, all communicating to each other as if they were literally plugged in together with an Ethernet switch. So that's essentially, there is no pseudo wire in this case. It's basically the MPLS cloud is acting as a layer 2 switch. All right. The VPLS service that's running emulates that Ethernet switch for every port that's connected to a different customer site. The PE routers are interconnected basically with a full mesh across the MPLS backbone of the service provider. We do self-learning of the source MAC address to port associations. Frames get forwarded based on destination MAC address, just like a switch. If the destination MAC address is unknown, or if we're sending a broadcast or multicast address, the frame gets flooded to all the ports associated with the virtual bridge. So the VPLS core acts very much like a real switch, right? Instead of setting up these point-to-point or point-to-multipoint connections. The frames get flooded to all ports, etc. All right? The VPLS core itself doesn't use the spanning tree protocol, but it does use split horizon when we're forwarding, so that Ethernet frames are never sent back out the pseudo wire that they were received on. So very much like we see with a switch, we never forward a frame out the same interface that we receive it on. All right? So two very distinctly different operating modes, VPWS versus VPLS. And you could probably imagine that there is an application for both of these in a lot of different environments. All right? VPLS does look like an Ethernet switch with layer 2 core issues, right? Stability in the network as it grows, right? That's one of the concerns that you need to address with this VPLS solution, right? You should check to see if there's an appropriate network design that's going to support future growth in that VPLS core. The impact of network outages is important to understand as well. You need to ask about what happens to the traffic if there's an outage in the core network, right? And you can create backup links and backdoor links and whatnot to facilitate communication, right? Multicast and broadcast traffic between the sites. Because VPLS acts like a switch, multicast and broadcasts get flooded as opposed to forwarded, right? Now, in the case of broadcast, that's never going to change. Broadcast traffic is always flooded by a switch. It's never forwarded by a switch. But you may have the ability to do something with the multicast traffic. Not in a sense like we would run, IGMP snooping or something like that in the VPLS core, but and because of that, that multicast traffic would get flooded just like the broadcast traffic. So you might want to segment off the network, with different VLANs or whatnot to ensure that the multicast flooding gets limited, or the broadcast flooding gets limited in some way. The other concern is IGP peering scalability. Because it's a single broadcast domain, all the attached routers are going to be typically routing peers, right? Now, in the case of OSPF, that's not totally the case. They won't be full peers. They might be two-way peers because we would do a DR-BDR election in that environment. But as the number of routing peers increases, this becomes a little bit of a scaling problem, right? Because now I've got this logarithmic or exponential growth of peering relationships based on the number of routers that are connected to that VPLS core. And the only protocol that's really designed for a large number of peers is BGP. Now, that's a relative discussion, isn't it? Because large, in a sense, is that we're talking about here is potentially tens of thousands of peers, right? But it's not necessarily, 1,000 peers or 500 peers. To some people, 500 peers might be considered a large environment. We know that EIGRP and OSPF can scale up to that level, so BGP may not be necessary in that case. All right? But you should consider using BGP if you have a really, really large VPLS network. There is also the consideration of the impact of spanning tree or loops of another customer. Remember, in VPLS, even though it is virtually private, we are doing something called statistical multiplexing, right? And all customers are sharing bandwidth on the on the links, right, on that VPLS cloud. Because of that, you have to ask about the impact of a customer that doesn't design or deploy their network correctly. If they create a spanning tree loop, what would be the effect on your network, right? If a customer is attached via a layer 2 switch, all the packets from the loop would be flooded with all the links that are interconnecting their VPLS sites. And, if they're connecting at 1 gig or 100 meg and the provider trunks are 20 gigs or maybe even a gig or 10 gigs, the impact might not be critical. But if the provider links are 2 gigs, then all of a sudden the provider's network gets saturated with too much traffic. So you may, even though the traffic is virtually separated, it doesn't necessarily mean that it is, the effects of broadcasts are isolated from the other hosts, all right? They're not necessarily isolated. The other thing to consider too is there may be some layer 2 security concerns as well. Since all the traffic from all the customers is going over the same core network, we need to make sure that that the service provider has implemented some sort of layer 2 security measure so that one customer can't see other customers' traffic. All right. Now, most service providers are going to pretty much guarantee this, if they're worth anything in their, deployment, so they're worth anything in value to their customers, they're going to provide you an understanding of how they're providing those security mechanisms. The other thing that we need to kind of address as part of the overall discussion of VPLS design is the scalability of VPLS, right? There are several different scaling factors that play a role in how large a VPLS network can grow to, or how large it can become. And the first is, of course, scaling the full mesh of pseudo-wires between my PE devices, frame replication and frame forwarding, and MAC address table sizes. All right? Now, that's what it says on the slide, but let me go ahead and try and explain a little bit more in detail about each of these bullet points so that you have a better understanding of what we're actually talking about with regard to scalability. All right? So the first one here, as the number of PE devices grows, right, each edge device has to form adjacencies with all of the other provider edge devices. That adjacency requires that the edge device has an IP address of all of the other remote provider edge devices in its routing table. It's also going to require that all of the PE devices exchange label information between each other. So we have this, what we call N-1 control plane scaling issue. As we add more and more and more PE devices, we have to have more and more information that's stored on those PE devices about the pseudo wires, about the endpoints themselves. We can kind of see in the diagram here a representation of the pseudo wires connecting the PE devices in the core. Remember, with VPLS, every PE device is able to communicate to every other PE device. So it becomes basically a big switch in the middle. Well, that's going to require a full mesh of connectivity. The second bullet point, which is frame replication and forwarding. All right. Now, we already talked about how VPLS forwards Ethernet frames by using MAC addresses. Very much the same that you might see with bridges or switches in the past. all right? The switch learns the source MAC address to port mappings or port associations, and it forwards the frames based on the destination MAC if the destination address is unknown, or if it's a broadcast or unbounded unicast or multicast, the frame gets flooded to all the ports associated to that particular bridge. In this case, that would be every other PE device on the network. So you can see where a large amount of broadcast traffic or a large number of pseudo wires connecting different PE locations could potentially, well, not really scale well in the grand scheme of things, right? The more endpoints we have, the more pseudo wires we have, the more we have to scale this environment. All right? And the last thing, and really one of the biggest considerations is designing the MAC address learning aspect of the VPLS provider network. PE devices need to be capable of managing MAC address tables for lots and lots of customer devices. And on top of that, lots and lots of customers. Much more than, say, you would as a typical enterprise campus switch managing just your local Ethernet devices. All right? Now, to address all of these concerns, these scaling issues that we just talked about, there was another type of VPLS introduced called the hierarchical VPLS. And HVPLS introduces design elements that reduce the signal overhead and the packet replication requirements for the PE devices. It doesn't have anything to do with the CE devices. We're just talking about scaling ability and scaling factors for the provider edge devices. Two types of provider edge devices are defined in this particular HVPLS model. User-facing provider edge, which is called the UPE device. All right? UPE stands for the user provider edge, and that's going to be the user-facing device. And then we have the NPE device, the network provider edge device. And that's going to be connecting to the network side, right? And we see that demarcation here on the diagram. Here's the UPE, which is the customer side. Here's the NPE, which is the network side. Remember, this is all part of this hierarchical VPS deployment model. All right? Customer edge devices connect to UPEs so that they can aggregate VPLS traffic before it reaches the NPE where the VPLS forwarding takes place. Now, the whole point of this is to address some of the scaling factors or scaling issues that we saw with traditional VPLS design, right? Scaling of the full mesh of pseudo wires between the PE devices, right? How does HVPLS address that? Well, it helps address that issue by using the UPE devices to spread the network edge workload across multiple devices that might be less costly or more easily deployed, right? This is going to lower the number of pseudo wires between the NPE devices, and it's going to help us scale the network by reducing that burden on the core for the frame replication and frame forwarding options. I don't know if that makes sense, but hopefully it gives you an idea. This UPE device, you can kind of see it in the diagram here. So instead of having two customer edge devices connected into the VPLS core, we've got a single UPE device which acts as an aggregate for several customer edge devices. All right? Which means that we have to have fewer pseudo wires, right? Because we don't have as many customer edge devices connecting to the VPLS network. All right? If you look at this from the perspective of frame replication and frame forwarding, we need a lower number of pseudo wires as well, because only the NPE devices are connected in a full mesh, as opposed to every CE device or PE device that might be connected at each branch location. All right, so that's going to reduce the burden on the core for things like frame replication and frame forwarding. The MAC address tables are spread across multiple devices at the edge. The UPE devices only need to learn the MAC addresses or learn the local NPE devices, and they don't need a large routing table to support connectivity. The core NPE devices still need to manage very large MAC address tables, but using this MPLS in the core removes the MAC learning requirement from the provider devices and extends it to these NPE devices. It gets a little complicated, right, when you start to add all of this hierarchical design to this process. But again, this would be something that would be required if you have a very, very large VPLS deployment. In smaller VPLS deployments, this hierarchical design is not really necessary because we can address a lot of the scalability factors just by reducing the scale of the design. All right. All right. Now, another issue that we run into with VPLS is the scalability of our IGPs, our interior gateway routing protocols. All routers that are attached to the VPLS network see the segment as a broadcast segment, which means the IGP protocol acts as if there are lots and lots of routers connected at the same time to that broadcast domain. If we're using OSPF as a routing protocol, we use a few neighbors in the same broadcast segment. At least that's the general recommendation, right? No router should have more than, say, 60 neighbors. But in a VPLS deployment, that number can be reached pretty quickly. The other issue that comes up is if some sites experience packet loss, all of a sudden OSPF processing, rerunning calculations, rerunning the algorithm, going through the shortest path first algorithm can consume a lot of CPU cycles on the routers in that segment. Especially if you have links that are flapping or you have lots of changes in the topology. Another issue that can come up is the instability in the VPLS network is, or that results in the instability of the VPLS network, is the loss of connectivity between a DR and a BDR. Remember, we're going to do a designated router and a backup designated router election in this process. You know, the whole point of the DR-BDR election is to reduce the number of full adjacencies that are required on a multi-access network, like a broadcast segment. But when the routers are connected to VPLS, they elect one of the routers as the DR. We know that from our basic OSPF discussion that all the other routers in that broadcast domain form a full adjacency with that particular router. If there is connectivity lost between the DR and the BDR, though, in other words, the BDR can no longer see the DR, the BDR is going to promote itself to the DR. Now, in a physical switch, this is very, very unlikely to occur. But when we're dealing with VPLS and pseudo wires, it is a possibility that this could occur. And then all of a sudden, you're going to have two DRs in this environment. Okay? Now, this can cause, obviously, a lot of issues, and because of these reasons, because we talked about the number of neighbors that you can have, because of the processing overhead that OSPF introduces as a link state protocol, because of the DR and VDR election process that exists, OSPF is a little bit less preferred for a VPLS network than maybe some other routing protocols. All right? I mean, EIGRP still suffers from the same similar restrictions, right? We can't have a large number of peers in EIGRP either, but we don't have to deal with the DR-BDR election process. So what are the choices? Well, the choices is partitioning the network so that we reduce the number of adjacencies that might exist, or the other option is to run BGP because it's more suited to support multiple peers in the network, in the design. All of the stuff I'm talking about kind of makes it feel like, or it makes it seem like VPLS is really not a good solution, right? We have a lot of caveats and a lot of restrictions that we're applying to this design. But there are some advantages to running VPLS as well. The biggest advantage of using VPLS is that MPLS is only used for data plane connectivity and not for control plane connectivity, right? If there's a failure in the P network, the traffic automatically gets rerouted along available backup paths in the P network because it's essentially a layer 2 network, okay? There is a cost for this fast failover, right? Having redundant pseudo wires, and if those redundant pseudo wires are used to form these redundant PE or paths between the PE devices, we might have to age out MAC addresses, followed by maybe some unicast flooding for the unknown MAC addresses. So that result might be lost packets followed by a surge of traffic, which is obviously going to have kind of a negative impact on our overall performance of our network. We can use pseudo-wire rerouting, although I have to say pseudo-wire rerouting increases the availability of the VPLS service inside the provider network because it allows us those alternate paths. It doesn't really protect against local loops or CE device failures. It only allows us to ensure switching or data plane protection across the VPLS network. All right. All right. So what is the difference? I mean, we've talked about VPLS. We've talked about VPWS. Why would I consider one versus the other? And, you know, in summary, what are we talking about, the difference between these two, right? Both VPLS and VPWS provide different functionality and different features. They both offer layer 2 connectivity. We know that one does it a little bit different than the other, right? VPWS is more of a point-to-point technology. Each PE router has a pseudo-wire connection to other PE routers. But because it is a point-to-point technology, you need a pseudo-wire to each remote site. So this obviously introduces scalability issues, especially if you have lots and lots of remote sites. VPLS can overcome that issue because it does point-to-multipoint connections, not just point-to-point connections. Also, because VPWS is a point-to-point technology and VPLS is point-to-multipoint, it means that the requirements on the CE devices change, right? Whether or not you're running VPLS or VPWS. If I'm running VPWS, the CE devices have to do the switching themselves, which means that the CE device has to choose which pseudo wire it should use and what PW it should use to send the data to the remote site. In VPLS, we simply send the data, and that's destined for a remote site to the PE router, and it's the PE router's responsibility to decide where to send that traffic, not the CE router's responsibility. All right? That's because VPLS acts like an Ethernet switch. But because it does, it also has to provide a lot of the features that are core functions of the network switch. Besides forwarding, it has to take care of loop prevention, dynamic MAC address learning so that we can make sure that we're forwarding frames correctly to the remote sites, MAC address aging. So in this particular case, it's pretty clear that the PE routers have to perform more tasks that wouldn't necessarily be required in a VPWS environment. VPWS can be the primary choice when we want to connect a few remote sites. So we want to use VPWS, for example, when we want to bridge 2 data centers in the same layer 2 network. All right. But if you configure the hub and spoke topology, you can configure point-to-point connections to each site from the hub router. We can also configure point-to-multipoint on the hub side and point-to-point on the spoke sides. All right. So we can kind of mix the deployment topology there. Hopefully that gives you kind of an idea of the different layer 2 MPLS VPN options. We talked, of course, initially about all of the layer 3 MPLS VPN options, but now we're talking about the layer 2 MPLS VPN options. So in this chapter of this module, we talked about the major decision points for choosing different WAN connections, the financial, the technical decision points that we're dealing with. We talked about a layer 3 MPLS VPN and how that provides layer 3 connectivity over the MPLS provider network, and talked about all the parts and the components that are involved in kind of facilitating that communication. We can use different protocols for our CE to PE link. We talked about the impact of using EIGRP, OSPF, BGP. iBGP is used in this case to transfer customer routes from one site to the other site in our layer 3 MPLS VPN. MPLS labels, we talked about how those are used to forward data in the provider network for our layer 3 MPLS VPN switching function. And then we looked at VPWS, providing that point-to-point pseudo-wire connectivity between our layer 2 sites. And then we talked about the VPLS providing the point-to-multipoint function, much like a regular switch does in a LAN environment. All right? And that concludes that lesson.